talk about derivatives of logarithms. So if you recall, when we have log base a of x equals y, that means that a raised to the y is equal to x. The base of your logarithm is the base of the exponential expression. Your logarithm is equal to an exponent. So this logarithm gives you that exponent of a. And what you're taking the logarithm of is the result of taking a raised to that exponent y. Remember, we have those two special logarithms, your common log, which is base 10, which has no number written here, and the natural log, which is base e, which also has no number written here, but that number is an e. These are different. Log is base 10. ln for log natural log is base e. Remember your change of base formula. If you wanted to take log base a of x and turn it into any other base, like the natural log, it would be the natural log of what you were taking the logarithm of divided by the natural log of the original base a. Properties of logarithms, remember, if you're taking the logarithm of two things being multiplied, you can break it up into the logarithm of the first plus the logarithm of the second. If you're taking the logarithm of two things being divided, it's the logarithm of the numerator minus the logarithm of the denominator. And if what you're taking the logarithm of is all being raised to a power, you can bring that power out front and it becomes a coefficient. These are properties that you should have learned in some sort of an advanced algebra or pre-calculus type class. If you need help with these, then please seek out some other resources. You can also send me an email and I can send you some videos that go over these properties of logarithms. So the derivative of the natural logarithm. If you are taking the derivative of the natural log of a function of x, then it's the derivative of that function of x over that function of x. Notice you're taking the derivative of the natural log of this function f of x. This exact function f of x goes on the bottom. The derivative of this function f of x will go up here on the top. And notice the natural log itself inadvertently goes away. I do have a shorthand for this. I say if your function is the natural log of some inside function, then its derivative is the derivative of that inside function over that inside function. All right, so let's go through some examples. Let's take the derivative of the natural log of x. So you're taking the natural log of x. The inside function is x. What's the derivative of x? 1. So its derivative will be 1 over x. You have the inside function on the bottom and the derivative of that inside function up top. All right, here, if we were going to take the derivative of the natural log of 3x squared minus 5x plus 7, we're taking the natural log of an inside function. This whole thing here is my inside function. I can call that I. Then I can use my 4 basic derivative rules to take the derivative of I to get 6x minus 5. The derivative of g will be the derivative of the inside function over the inside function. I have the inside function, I have the derivative of the inside function, plug them in, and I get the derivative as 6x minus 5 over 3x squared minus 5x plus 7. Let's look at the natural log of t to the negative 4 minus 5t to the negative 2 plus the square root of t. As we've done before, anytime you have a radical, you're going to want to get rid of that radical and write it as a fraction exponent. Now we have the natural log of an inside function. So the derivative will be the derivative of that inside function over that inside function. So if you want, on the side, you can say, okay, that t to the negative 4 minus 5t to the negative 2 plus t to the 1/2 is my inside function. Use your 4 basic derivative rules to get the derivative of that inside function. Then you have the two components that you need for the derivative of s of t, the derivative of the inside function over the inside function. Here, what do we have? We have y equals x squared times the natural log of x. Variable times variable. X squared times the natural log of x. Here, you're going to have to use the product rule. So remember your product rule is the derivative of the first, which the first is going to be x squared, times the second, and the second is going to be the natural log of x, plus the first times the derivative of the second. So if you want, on the side, you can label your first as x squared. The derivative of that would be 2x. Your second would be the natural log of x, and the derivative of that would be 1 over x. And then you can plug them into your little formula, f prime s plus f s prime. So we have 2x times the natural log of x plus x squared times 1 over x. One of these x's is going to cancel, and that will simplify to 2x times the natural log of x plus x. It's a Look at another example. C of x equals the natural log of x over x cubed. Look at what we have here. Natural log of x over x cubed. Variable over variable. You're going to have to use your quotient rule here. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. On top we have the natural log of x. The derivative of that is 1 over x. On the bottom we have x cubed, and the derivative of that is 3x squared. So now we have t prime b, t, b prime, and b. We can plug those all into our formula. The derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Now let's simplify this a little. This x and one of these x's is going to cancel here, and I'm just going to switch these. I'm going to pull this 3x squared out front. Now both of these have an x squared here. I'm going to pull one of those x squareds out. X cubed squared becomes x to the 6th, and I have 2 x's up here and 6 x's down there. 2 of them are going to cancel, and I get a final answer of 1 minus 3 times the natural log of x all over x to the 4th. Let's keep going. Let's look at h of x equals 5x squared minus 4 times the natural log of 3x to the 6th minus 9x squared plus 11 minus 17. Sum and difference rule says if you can take the derivative of each of the pieces, then you can take the derivative of the whole. It's just that when I take the derivative of this middle piece here, I will have to use my little I prime over I. So the derivative of 5x squared is 10x. That 4 is a coefficient times the derivative of the inside over the inside minus the derivative of 17 is 0. So now I'm just going to replace I with the 3x squared minus 3x to the 6th minus 9x squared plus 11 on the bottom. And the derivative of that, which would be 18x to the 5th minus 18x on top. There's no need to carry that minus 0. I just drop it. And now what we can do, this is really 4 over 1. So I'll do 4 times the entire numerator, 1 times the entire denominator, to get a more simplified answer of 10x minus 72x to the 5th minus 72x all over 3x to the 6th minus 9x squared plus 11. Let's look at this one. P equals the natural log of the square root of q. First things first, we need to get rid of that square root, so we'll call that q to the 1/2. So I'm taking the derivative of the natural log of an inside function. The inside function happens to be q to the 1/2. So we'll take the derivative of the inside function, 1/2 q to the negative 1/2, over the inside function, which is q to the 1/2. But we can simplify this. Like bases being divided, I can subtract their exponents. So that gives me 1/2 q to the negative 1/2 minus 1/2, which gives me negative 1. To get rid of that negative exponent, I'll move it to the other side of the fraction bar, and that becomes 1 over q. So I have 1 over 2 times 1 over q, or that my derivative was 1 over 2q. Now that was a lot of work. There's another way to solve that same problem. So let's look at it again. The natural log of the square root of q. That's really the natural log of q to the 1/2. But if you know your properties of logarithms, then you know that the logarithm, what we're taking the logarithm of is being raised to a power. I can bring that power out front and make it a coefficient. So now I have 1/2 times the natural log of q. So now this 1/2 is just a coefficient, and coefficients multiply in at the end. So now that I go to take my derivative, it'll be 1/2 times the derivative of the natural log of q, which is 1 over q, and that gives me that same answer of 1 over 2q. So the important thing here is, whenever possible, you're going to want to expand your logarithm first. Use those properties of logarithms to expand your logarithm into as many logarithms as you can. Try to do as many as you can with no exponents, if possible, and then take the derivative. And that'll make your life so much easier. You don't have to do as much work. Let's look at another example. Let's look at the natural log of 4x minus 3 all over 7x squared plus 11x. If I just did the derivative of this, I prime over I, my inside function is this whole thing, 4x minus 3 over 7x squared plus 11x. When I go to take the derivative, I prime, I would have to use the quotient rule. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And all of that would just be my I prime, and it would still all be over this. and then we would have to reduce. But we can use the properties because we have a natural log right here. We have that property that says if you're taking the logarithm of two things being divided, it's the logarithm of the numerator minus the logarithm of the denominator. By breaking them up into two separate logarithms, I just got rid of having to use the quotient rule. So now I can take the derivative of this minus the derivative of this. And when I do the derivative of this, it'll just be the derivative of the inside function over the inside function minus, when I take the derivative of this, it'll be the derivative of the inside function over the inside function. And that was a whole lot easier than trying to do your quotient rule inside your I prime over I. Let's look at another example. The natural log of 7x to the fourth minus 9x cubed minus 7x plus 1 times 8x cubed plus 4x squared minus 12x, all of that being raised to the third power. Now, if I was going to do I prime over I, the derivative of the inside over the inside, notice this whole big thing right here is my inside function. To take the derivative of that, I've got chain rule, and inside my power chain rule, I would have product rule. That seems pretty messy. So instead, let's use those properties of logarithms to expand this into as many logarithms as we can. What you're taking the logarithm of is all being raised to a power. We can bring that power out front and make it a coefficient. That just got rid of chain rule. Now you're taking the logarithm of two things being multiplied. I can break that up into two logarithms being added. The logarithm of the first plus the logarithm of the second. Notice this 3 will carry to both. So now I just got rid of product rule. So now I have 3 times the derivative of this plus 3 times the derivative of that. So now I'm ready to take my derivative where that 3 is just a coefficient. So inside function goes on the bottom, derivative of the inside function up top. Minus that 3 carries through, inside function on the bottom, derivative of the inside function on the top. We'll pause here and we'll continue this lesson in our next video. See you next time.